Hello, welcome. This is the second video of this playlist about the preparation of imidazoles. In this video we'll have a look at the properties and uses of benzimidazoles and at some practical methods to prepare them. Benzimidazoles are similarly stable as imidazoles. Although these heterocycles are formally carboxylic acid derivatives, hydrolysis is difficult. According to an older article, simple benzimidazoles could not be cleaved neither by hydrochloric nor hydroiodic acid, nor by sodium and ethanol. Only very electron-deficient or electron-rich benzimidazoles will be easy to hydrolyze. One cleavage strategy is treatment with benzoyl chloride and aqueous caustic, and I'll show you an example later. Benzimidazoles are more stable and easier to prepare than substituted naphthalines and are therefore an important substructure of drugs and biocides. Here are 4 famous benzimidazole-containing drugs, but many more are known. Benzimidazoles are best prepared from 1,2-diaminobenzenes or 2-nitroanilines by cyclocondensation with carboxylic acid derivatives, aldehydes, alcohols, amines, or alkyl halides. Because of the high resonance energy of imidazoles, intermediate imidazolines are easy to oxidize and sometimes aromatize spontaneously without any added oxidant. Nitroanilines are accessible by aromatic nucleophilic substitution or by nitration or nitrosation of anilines. Another strategy is cyclization of 2-haloaryl amidines, either by transition metal catalysis or by aromatic nucleophilic substitution. Then N-aryl amidines can cyclize to benzimidazoles when treated with oxidants, for instance hypochlorite. I'll show you now some examples of each of these strategies. Here a benzaldehyde was condensed with diaminobenzene without any oxidant, and a high yield of benzimidazole resulted. To prevent formation of a byproduct benzylated at nitrogen, the starting aldehyde was deactivated by conversion into a bisulfide adduct. Later in the section about side reactions we'll see how this byproduct was formed. In this example the condensation was run in the presence of air, and again a high yield of benzimidazole resulted. Reactions with aliphatic aldehydes can cause more problems because of self-condensation of the aldehyde. Here benzimidazole formation was achieved at room temperature with an excess of thionyl chloride as dehydrating and oxidizing reagent. With oxone as oxidant, cyclization and oxidation can also proceed at low temperature under relatively mild conditions. 1,2-bis-alkylaminobenzenes can be cyclized to benzimidazoles under mildly oxidizing conditions, as shown here. An imine was formed initially, which cyclized to an imidazoline and then aromatized. Instead of diaminobenzenes, also 2-nitroanilines can react with aldehydes to the corresponding benzimidazoles. Here this reaction was mediated by an excess of sodium dithionide, a reducing agent which tends to initiate radical chain reactions. Also carboxylic acids can convert diaminobenzenes into benzimidazoles, but these reactions do not proceed as readily as the condensation with aldehydes. The first step is formation of an amide, and this requires stronger heating than the formation of an imine. In this example, the parent benzimidazole was prepared by refluxing diaminobenzene and formic acid for 2 hours. Similarly, trifluoromethylbenzimidazole can be prepared by heating diaminobenzene and trifluoroacetic acid in aqueous hydrochloric acid. If instead of the unactivated carboxylic acid an anhydride or acyl chloride is used, benzimidazole formation may proceed under milder conditions. Here acylation of a protected diaminopyridine with chloroacetic anhydride gave a fair yield of the pyridoimidazole after 3 days at 30 degrees Celsius. Amides and esters can also be condensed with diaminobenzenes. In this example, heating chlorodiaminobenzene with an excess of DMF, acylane and catalytic zinc acetate yielded only the expected benzimidazole. With nitrodiaminobenzene, however, the main product was an N-methylbenzimidazole. The same result was obtained with N-diethylformamide, what indicates that the methyl group was formed by reduction of some formic acid derivative. Lactams, like formamides, are more reactive than simple non-cyclic amides. Here, a particularly electron-rich diaminobenzene was acylated by NMP. Reflux with an excess of aqueous hydrochloric acid and catalytic sulfide brought about benzimidazole formation. Also, nitriles can serve as carboxylic acid equivalent for the preparation of benzimidazoles. Under the optimized conditions shown here, thiabendazole was obtained in high yield, again under acidic reaction conditions. In this example, a benzimidazole was prepared by acylating a diaminobenzene once and then cyclizing the amide by heating with acetic acid. Upon single acylation, the reactivity of the remaining unacylated amino group of 1,2-diaminobenzenes drops, and such monoacylations give therefore higher yields than that of non-conjugated diamines. It is also possible to reduce and cyclize acylated 2-nitroanilines. In this example, catalytic hydrogenation yielded a hydroxyimidazoline, which did not aromatize spontaneously and had to be heated with concentrated hydrochloric acid to eliminate water. 2-nitroanilines, by the way, are poor nucleophiles and difficult to acylate. Benzylic alcohols are readily oxidized to benzaldehydes, in particular under alkaline conditions. Here, benzaldehyde was generated from benzyl alcohol and then condensed with a substituted 2-nitroaniline. Similarly, amines can be oxidized to imines, which can act as synthetic equivalents of aldehydes. In this example, treatment of 2-nitroaniline with an excess of dibutylamine and catalytic iron trichloride and sulfur yielded 2-propyl benzimidazole. With primary amines, however, this procedure gave a mixture of a pyracene and a benzimidazole. When diaminobenzenes are condensed with carbonic acid derivatives, either 2 benzimidazolones or 2 heterosubstituted benzimidazoles result. In this example, treatment of 1,2-diaminobenzene with tetraethyl orthocarbonate yielded 2-ethoxybenzimidazole. Similarly, 2-mercaptobenzimidazole has been prepared from diaminobenzene and ethyl xanthate. Acetoacetates are readily cleaved by nucleophiles. Interestingly, strong heating of diaminobenzene with ethyl acetoacetate yielded mostly N-propenyl benzimidazolone, with some 2-methylbenzimidazole as byproduct. This byproduct became the main product when the reaction was conducted in refluxing toluene with an imidazolium salt as catalyst. Here are further conditions suitable for the preparation of the N-propenyl benzimidazolone. This product was probably formed by ring contraction of a benzodiazepine, as sketched here. Even simple ketones can undergo CC bond cleavage upon reaction with diaminobenzenes, as in this example. The driving force was the high resonance stabilization of imidazoles. In this case, a methyl anion was released from the intermediate imidazoline and trapped by iodine. I've sketched here one possible mechanism where this methyl group would end up as formaldehyde. Because of the high stability of imidazoles, imidazolines, like dihydropyridines, are good hydride donors and can be used as reducing agents. Here, phenacyl bromide was reduced to acetophenone by reaction with a benzimidazoline. Instead of diaminobenzenes or nitroanilines, also 2 haloanilines can be transformed into benzimidazoles. Uncatalyzed aromatic nucleophilic substitutions will only proceed well with electron-deficient arenes. Otherwise, transition metal catalysis will be required, as in this example. Complexes of copper, nickel or palladium are most commonly used. Here 2-bromoaniline was condensed with isobutyraldehyde and upon treatment with sodium acide and catalytic copper 2-isopropyl benzimidazole resulted. As shown here, 2-iodo and 2-bromoaryl amidines can be cyclized in high yield by heating with a copper catalyst, while aryl chlorides are much less reactive. In this example, a 2-bromophenyl thiourea was first methylated at sulfur and then cyclized to a benzimidazole with the aid of a copper catalyst. Without methylation at sulfur, however, this same thiourea cyclized to a benzothiazole, not a benzimidazole. The most elegant and inexpensive way to prepare benzimidazoles is by oxidation of N-aryl amidines. Amidines can be prepared directly from anilines and nitriles, as in this example, or by first converting a nitrile into an amino ether, which is then treated with an aniline. When hypochlorite is added to such amidines, a fast chlorination at nitrogen occurs, followed by a slower cyclization to the benzimidazole, as shown here. This example is an optimized procedure for the preparation of thiabendazole. Chlorination and benzimidazole formation occurred in one step. To prevent chlorination of the product at carbon, less than one equivalent of hypochlorite was used at the beginning of the chlorination. The cyclization was then brought about by adding the remainder of hypochlorite and heating to 65 degrees Celsius for 1 hour. Another type of oxidative benzimidazole formation is the reaction of N-aryl imines with a silyl acid and a hydroperoxide, as in this example. Just as a curiosity, benzimidazoles can be formed by simultaneous imidazole and benzene ring formation from alpha-beta unsaturated aldehydes and an excess of cyanomethylpyridinium salts. This reaction probably proceeded by twofold addition of the activated nitrile to the aldehyde, followed by a series of cyclizations and eliminations. The scope of this strategy is narrow, though. If only a slight excess of cyanomethylpyridinium iodide was used, instead of a benzimidazole, a low yield of an aminopyridine resulted. Examples have also been reported of the electrophilic halogenation and nitration of benzimidazoles. In this example, both arenes of 2-benzyl-benzimidazole were nitrated under standard nitration conditions. Benzimidazoles and benzimidazolium salts are acidic at position 2, and electrophiles often attack this position. Here, 1-methylbenzimidazole was trifluoroacetylated in high yield and under mild conditions. Simple unactivated olefins can alkylate benzimidazoles at position 2. Here, such an alkylation was catalyzed by a rhodium complex. With electron-deficient alkenes, however, both branched or linear products may result. In these two examples, the benzimidazoles added to the less electron-deficient carbon atom of the alkene. Terz-butyl acrylate, on the other hand, mostly gave a linear product under these conditions. Then, benzimidazoles can of course be alkylated at nitrogen with alkyl halides, epoxides, electron-deficient alkenes, and related electrophiles. No strong bases are required. In this example, alkylation at nitrogen was faster than the alkylation of a primary hydroxy group. Alkyl iodides and bromides react with nucleophiles much faster than alkyl chlorides. Here, alkylation with bromochloroethane mainly yielded a chloroethyl benzimidazole and only small amounts of products resulting from chloride displacement. Let's check some potential side reactions. If the reduction conditions of nitroanilytes are too mild, dehydration to the benzimidazole may be slow and may require an additional treatment with acids or bases. Then, the reduction of nitro groups proceeds by intermediate formation of highly nucleophilic hydroxylamines. These can cause the formation of benzimidazole N-oxides, as in this example. A higher reaction temperature or acid or base catalysis can help to suppress these byproducts. If nitro groups are reduced by single electron transfer, the intermediate radicals can cause various side reactions, for instance dealkylations, as in this example with dithionite as reducing agent. The imines resulting from diaminobenzenes and an excess of aldehyde can cyclize and aromatize as sketched here, without the need of any additional reducing or oxidizing reagent. This can be prevented by first converting the aldehyde into a less reactive bisulfite adduct. I've shown you an example at the beginning of this video. Despite the high stability of imidazoles and benzimidazoles, these can sometimes be cleaved by treatment with strong electrophiles. Schotten-Baumann acylation with benzoyl chloride, for instance, causes ring cleavage of benzimidazole. In part 3 of this playlist, there's a similar example of the hydrolytic cleavage of an imidazole during bromination. Here are some further references which you can also find in the description of this video. Under the Community tab of my channel, there's a PDF version of the slides. The next video of this playlist is about the preparation of imidazoles from other imidazoles by substitution of hydrogen. This includes halogenations, acylations, alkylations and arylations. So long!